to remove the prostate, or with radiation therapy, or in case of really low-grade tumors, it's just watchful waiting, nothing is done. However, when the treatment is done, that is a radical prostatectomy or radiation therapy, the majority of the tumors are cured, and the survival rate is really high for most of the people. However, recurrence is seen in 20 to 30% of patients, and it's those patients that we have to worry about. So I'm not a clinician, I'm a basic scientist, and I would like to introduce you to the treatment of prostate cancer by pointing out that prostate cancer is regulated by the androgen receptor, and the androgen receptor is a transcription factor, and it consists of a ligand binding domain and an N-terminal and a DNA binding domain, which kind of looks like this. And it's inactive in the cytoplasm, but when it goes into the nucleus, it is activated. As I told you, it's a transcription factor. And the area in the target genes that it binds is called the androgen response element, which is a bipartite section which kind of looks like this. This is specific for PSA, or prostate-specific antigen, that I mentioned earlier, where N represents just about any nucleotide. So, the anti-androgens that are introduced and those that prevent the progression of prostate cancer are usually directed to bind to the ligand binding domain. So this is how the androgen receptor works. So androgens, which are outside of the cell, bind to the androgen receptor, and they are transported into the nucleus, and there are a series of co-regulators, either activators or repressors, that bind to the complex of the androgen receptor, and then they allow the transcription of the target genes. So prostate cancer can be caused by multiple reasons. One of the most common reasons is increased production of anti-androgens. Here I'm looking at dihydrotestosterone, which is the most powerful androgen. Also, the androgen receptor can be activated in a ligand-independent manner by either phosphorylation or a mutation or gene amplification or altered co-regulator function. And prostate cancer occasionally, very occasionally, also results from the activation of pathways that bypass the androgen receptor. So, going back to the tumors that recurred, initially they are hormone sensitive, and so the most common way of treating prostate cancer when it has recurred, or whether when it has spread outside of the prostate, is by androgen deprivation. And there are a lot of different ways by which androgen deprivation can take place. So orchiectomy used to be the most common way, which is castration, and giving estrogens or using LHRH analogs or antagonists are also ways by which androgen deprivation takes place. Then there are the use of anti-androgens, especially glutamide, which seems to be very popular until recently. When the tumor becomes resistant to these treatments, it's called hormone resistant, and when it becomes resistant to the anti-androgens also, it's called castration resistant. So most of the time that follows the metastasis to nearby regions, usually in the pelvis region, and following that, castration-resistant prostate cancer has recently received a boost, and there are a lot of new therapies that have been developed, including immunotherapy, radiotherapy, different kinds of chemotherapy, and a number of second-generation anti-androgens. But eventually, the tumor relapses and all of those treatments become ineffective. And what I want to point out is that the longer it takes to reach resistance, the better off the patient is. And so in my lab, we try to prolong the effectiveness of the anti-androgens. So we use animal models. We take human tumors from patients that have been resected by the surgeon, and we put them in mice to develop patient-derived xenografts. And those are usually, at the beginning, hormone sensitive. Sometimes we try to get cell lines out of those. And then the hormone-sensitive tumors are put into more mice. The mice are castrated, and we get castration-resistant tumors. But today I will talk about two established castration-resistant lines that were derived from CWR22 xenografts, which are androgen-dependent, to give rise to two tumors, CWR1 and 22RV1, which are both castration-resistant. What we saw is that although they are derived from two different labs, they came from the same origin. However, when we try to compare the molecular characterization of those two tumors, we found that they are very, very different. So when we compared those two cell lines, we found that only 60% of the genes expressed in those tumors were the same. The 40% were very different. And so we compared the 22RV1s with the CWRR1s in the presence of androgen, which is AD, and in the absence of androgens, which is AD minus. What we found is that there are lots of regions of genes that are transcribed by the androgen receptor that are very different in the cell lines, even though they are from the same origin. So when we analyzed those genes, we found that the androgens that are regulating those tumors express different kinds of genes and activate different pathways. So the canonical pathways regulated by DHT are very different. For example, notch signaling happens to be extremely high in the 22RV1s, but not so in the CWRR1s. Similarly, the functional characteristics of the genes are also very different. So the same genes are being transcribed, even if they are the same, they are doing multiple things that are very different in the two cell lines. So from there we determined that the selective pressure of androgen ablation has different effects on castration resistance development at different sites. Now, translating that to the patient's scene, the same patient may have two different metastases in two different sites and would have absolutely different molecular characterizations, which would make it very difficult for that patient's tumor to be treated. So what we found is that these are all the different functions that we ascribe to the different gene groups. What we found is that there is one thing that is similar between all of those gene functions, and that is that they are all being regulated by the EGFR family. Mind you, I'm not talking about EGFR itself, I'm talking about the EGFR family. So the EGFR family consists of 4 members, as we know. Most of us study, we EGFR and ERB2, but ERB3 has very high expression in prostate cancer. So, in contrast, ERB4 is usually lost in prostate cancer. So, because ERB4 is lost and ERB3 is kinase dead, they have to partner with either EGFR or ERB2 in order to activate those pathways. But ERB3 is important because, as we all know, PI3 kinase is a very important player in the development of prostate cancer, and ERB3 is one of the most significant activators of PI3 kinase because it has 6 binding sites for the P85 complex. So even though all these different dimers are possible, because ERB4 is present, only these 4 remaining dimers are possible in prostate cancer. And what we found is that when we inhibit both EGFR and ERB2, then all of these dimers are inhibited. And this was published back in, I think, 2011, and that was done by my graduate student, Leechin. So what Leechin found is that ERB3 is expressed very little in normal prostate, but it's very high in prostate cancer. And she also found that ERB3 is regulated by the androgen receptor. So when she overexpressed androgen receptor in a cell line that lacked androgen receptor, ERB3 was completely shut down. So what we hypothesized then is that androgen receptor works by suppressing ERB3. And when the anti-androgens are used, then androgen receptor is suppressed, and so ERB3 can be activated. And that work was done by Salma Siddiqui, a postdoc in my lab. So this is more proof of the same thing. We took PC346C cells and we stripped them of androgens. And over a period of a week, the level of androgen receptor went down. And as the level of androgen receptor went down, the level of ERB3 went up. And that you can see by the level of ERB3 in tumors that were treated with the bicalutamide. So compared to control tumors, the bicalutamide-treated tumors had much more ERB3, showing that androgen receptor is a negative regulator of ERB3. And this was published in 2010 and showed that E3 ubiquitin ligase called NRDP1 is a mediator of this effect of androgen receptor on ERB3. So we studied NRDP1 in more details, and we found that it has actually 2 promoter regions, and each of those promoter regions express an androgen response element, which is very similar to known androgen receptor elements in known targets of the androgen receptor. So my students then developed a luciferase assay to test whether NRDP1, this is a chip assay actually. So they developed a chip assay to see if the androgen receptor binds to NRDP1, and it did. And this is a negative control which did not change. So charcoal stripping, which removes androgens and suppresses the androgen receptor activities, caused a huge decrease in NRDP1 levels, and adding GHT back increased NRDP1 levels, which showed, or androgen receptor binding to NRDP1, which showed that it is regulated by androgens. So we came up with this model which showed that in castration-sensitive cell lines, the androgen receptor upregulates NRDP1, and then NRDP1 then suppresses ERB3, And since ERB3 regulates cell growth, that is how the androgen receptor regulates cell growth. However, in castration-resistant cell lines, we figured that ERB3 can bypass the androgen receptor. There's no regulation of the androgen receptor of ERB3, and the androgen receptor must be using a different pathway to regulate cell growth. And this was published earlier this year by my other graduate student, Rosa Wender. So, in conclusion, the androgen receptor regulates many different pathways, which most of which has been known or published, and androgen ablation then stimulates those pathways, and because of that, the tumor grows back. However, they all do not follow the same pathway. They all tend to follow different pathways, which makes the suppression of the castration-resistant androgen receptor independent cell lines or tumors very difficult. So, because many of these pathways are regulated by the EGF receptor family of tyrosine kinases, our current project includes studies of both in preclinical and in clinical models, a study of EGF receptor inhibitors in combination with an AR antagonist, especially enzalutamide. And the person in my lab who's doing this is J.N.Tata, who's another graduate student. And this is my lab. As you can see, I have to look up at all my graduate students because they are all taller than me. My funding is from the National Cancer Institute and various other sources. So thank you very much.